Hi friends, today we'll discuss numericals on designing a Butterworth IR low pass filter using impulse invariant transformation technique. Let us take an example. Design Butterworth IR low pass filter using IIT where t equal to 1 seconds and some specifications are given. Using these specifications we have to design the filter using IIT. See, one standard procedure is there. In that procedure we have to follow some 6 steps. Using those 6 steps easily we are going to design Butterworth filter using IIT method. First step is specification of IR low pass filter. Specifications of IR low pass filter. There pass band edge frequency omega p is represented as omega p, stop band edge frequency omega s, gain in normal value nothing but not represented in decimal. At pass band edge is represented as ap. Similarly, gain in normal value not in dp. At stop band edge is represented as as. In this example, uh, it is given 0.707. It indicates that it is the gain in normal value at passband edge, so it is what 0.707. Similarly, omega p, that is passband edge frequency, is how much? It is given 0.35. This indicates that passband edge frequency, it is passband gain. Similarly, stop band edge frequency is given as 0.755 pi, and passband gain in normal value at stop band frequencies, that is as equal to 0.2. So from the given specifications we listed specifications of IR low pass filter. Those are omega p pass band frequency omega p equal to 0.35, stop band frequency omega is equal to 0.75 pi, and gain ap equal to 0.707, and stop band gain, that is pass band gain, it is stop band gain, that is as equal to 0.2. Next, specifications of uh, analog IR low pass filter. Those are gains remain same. Those are AP and AS. Pass band gain and stop band gain remain same. And using IIT technique, let us calculate the frequencies. Omega p equal to omega p by t, where t value is given, that is 1 seconds. So let us substitute. uh, Omega p is what? 0.3 pi divided by 1, that is pi equal to 3.142. So hence 0.3 into 3.142, we got 0.9425. Similarly, stop band frequency omega is equal to omega s divided by t, that is 0.75 pi. 0.75 into 3.142, we got 2.3562. Let us calculate the order of the filter. That is n equal to 1 by 2 log of 1 by a square minus 1 divided by 1 divided by ap square minus 1 whole divided by log of omega s by omega p. In some cases we also represent the same formula as 1 by 2 log of 1 by ap square minus 1 divided by 1 by a square minus 1 whole divided by log of omega p by omega s. Using this formula also we are getting the same order of the filter. There is no change in the result. Anything you can use this formula, or you can use this formula. Ultimately we are getting the same result. Hence let us substitute n equal to 1 by 2 log of as is given, that is 0.2 square minus 1 divided by 1 divided by ap is given, pass band gain, that is 0.707 whole square minus 1. Similarly, log of omega s stop band edge frequency, that is 1.9425 calculated, divided by 2.356. After simplifying this one, we are getting substitute and simplify, then we are getting order of the filter as n equal to minus 1.7339. We know that always order is positive value, so let us not consider minus value. Always order of the filter is positive value. And one more thing we have to remember, we have to round off the this fractional value to the next nearest integer value. Hence it is an 1.7339 is there. next nearest integer value is 2, hence round up to the next nearest integer value, that is n equal to 2, hence order of the filter becomes 2. Next step is step number 4, normalized transfer function. Finding the normalized transfer function. For that formula is h of sn equal to uh, summation k equal to 1 to n by 2. N indicates that order of the filter 1 divided by sn square plus bk sn plus 1. Then what bk indicates? How to calculate bk? Bk equal to 2 sine of 2k minus 1 into pi divided by 2n. Then what is the value of k? How to identify the value of k? K equal to n by 2. N is already calculated, that is 2. 2 by 2 is 1, hence we got k equal to 1. Substitute here k equal to 1. b1 equal to 2 sine of k equal to what? 1. 2 into uh, 1, that is 2. 2 minus 1 is 1. 1 into pi divided by order of the filter is calculated as 2. 2 into 2 4, that is pi by 4. 2 sine of pi by 4 is 1.4142, hence b1 equal to 1.4142. Let us substitute, hence h of sn equal to 1 divided by sn square. We calculated bk value here, that is substitute 1.4142 sn plus 1, hence it is the what? Normalized. It is the transfer function of normalized case. Normalized case means always pass standard frequency is 1 radians per second. Let us calculate transfer function for the unnormalized case. So next step is step number 5, calculation of what? Finding the transfer function of unnormalized case or unnormalized transfer function. H of s equal to h of sn, where sn is replaced by s by omega c. Omega c we have to calculate. The calculation of omega c is omega c equal to omega s divided by 1 by a square minus 1 whole to the power 1 by 2n. Regarding this, we discussed in the designing of Butterworth filter. Same thing I have taken here. Hence the next step is substitution of the values. Omega c equal to omega s is already calculated, that is 2.3562 divided by 1 by 0.2 square. As means stop and gain, 0.2 square minus 1, 1 divided by 2 into n. N is what? 2. 2 into 2 4, so it is 1 by 4. Simplification we are getting 1.0645, hence 1.0645 radians per second is the what? Our cutoff frequency. Step number 6 is wherever s is there, replace s by omega c. Already we discussed. s is replaced by s by omega c in the above equation. So that is h of s equal to 1 divided by s divided by 1.0645 whole square plus it is bk 1.4142. S is replaced by s divided by 1.0645 plus 1. The remaining part is what? Simplification. After simplifying, we are getting h of s equal to 1.1332 divided by s square plus 1.5054s plus 1.1332. It is the transfer function of unnormalized case of Butterworth filter. It is what? It is the transfer function of Butterworth filter. Let us convert this transfer function to digital transfer function. It is the analog transfer function. Let us convert this analog transfer function to digital transfer function using IIT. This is the previous step, that is nothing but it is the transfer function of analog filter. How to convert? Before converting, let us express in a standard format. H of s equal to same thing I have taken here. Um, now here it is of the form observe the denominator term s square plus 1.5054 s is there. It is a square plus b square plus 2ab form. So 2ab means here a is what? A square plus b square plus 2ab. 2ab means it is a, it is nothing but it is 2b. 2b equal to what? 1.5054, hence b equal to we got 0.7527. The above expression we can express like this. Numerator term is same. Next, coming to the denominator, uh, it is what? A square, it is what? 2ab. We calculated the value of b, hence a square plus 2ab plus b square. B square means this one, b square, adding this one and subtracting, there is no change in the result. So this term is nothing but a square plus b, a plus b whole square form. Then because of that reason I added this term and subtracted. There is no change in the result. Next, further step, uh, the underlying term we are going to represent as a plus b whole square. Next, this term after simplifying we are getting what, uh, 0.7527 whole square is nothing but 0.566. So after simplifying this one we are getting, uh, next, uh, next, we know that one standard form is there. We discussed that b divided by s plus a whole square plus b square. Let us express this expression in that format. Because of that reason it is what, s plus a whole square plus b square. Once again I'm telling b divided by s plus a whole square plus b square. So let us, in order to express in this format, what I am doing, I am multiplying the numerator, this b term, and denominator. So because of that reason this term is looks like a in that format. Hence, uh, simplifying this one we got like this. Next step is, as I told, see, we express in this format b divided by s plus a whole square plus b square. If you using IIT method, if you transform this to in z plane, we are getting the answer like this. Now, uh, what is the value of here? A equal to point, 7527. B equal to what? B equal to point, 7527. Same thing. So same thing. 1.5055. This one, this remains same, this remains same. It is of the form, once again I am writing, it is of the form b divided by s plus a whole square plus b square. Here a equal to, 0.7527 and b equal to, this one 0.7527. Both values are same here in this example. So hence, e to the power a, e to the power minus at is there. So substitute a value, and t is what, 1 second. Sine of bt, sine of bt, t is 1, so b is what, 0.7527 into 1, this much, into z raised to minus 1 divided by 1 minus 2 to the power e to, sorry, 2 into e to the power minus 8 is there. Once again same thing, cos of bt substituted, then plus 2 e to the power minus 2a, t is 1, z to the power minus 2. After simplifying this term, let us simplify this above, expression by setting your calculator in radian mode. Then you are getting the answer like this: h of z equal to 0.4848 z to the power minus 1 whole divided by 1 minus 0.6876 z to the power minus 1 plus 0.2219 z to the power minus 2. It is the transfer function of digital filter by using impulse invariance transformation. Hence this is the answer. Even also we can represent the answer in terms of positive powers of z. There is no, we can also express in negative powers as well as in, positive powers. Yes, thank you very much.